Consider a sinusoid, a discrete time sinusoid, that is x of n equals to cos 2 pi small f times n. Let's try to plot this signal x of n for different values of the small f. Now I need to plot x, that is cos 2 pi into small f into n. Now this integer, I'll take it in a range of say from 0 to 49, that is for 50 samples. You may increase the samples as per your requirement, and I want this small f to be varied in certain range. So let this small f be varied. So I'll have to have a for loop for f equals to, let's say f is being varied from 0 with a step of 0.1 till say till 1, and then I'm calculating x and then plotting it. Let me name. So the title would be the same as that of the f that we are having for each of the signals. So let that be num2 str, just because small f is a number. In order to display that, I'll require a string, so I'll simply convert that to string, and I'll type as f equals to whatever the value that f takes, the bracket complete. I need to plot each of these plots in various different subplots. So I'll write subplot. Now from 0 to 1, that makes around 11 figures. So I'll take, instead of 1, I'll take 1.1, so that makes 12 figures. So let's make an array of 6 by 2, and let a variable k indicate the figure number on which the signal would be plotted. Let k equals to 1, and k being varied from 1 onwards and gets incremented every time the signal is getting plotted. So if I run this program, I'm simply trying to plot the signal cos 2 pi fn for different values of small f. So you may see here, for different values of small f, I am getting different plots. As you may see here, the first plot here, let me zoom that. So this first plot here is for f equals to 0. So it's a straight line, just because the frequency is 0. The plot next to it is for small f equals to 0.1, that is 10 samples per 1 cycle. So you may see that there are 10 samples per 1 cycle, and so on. So as we go down this figure, the f increases. So this is for f equals to 2. On the right we have for f equals to 3, and so on. You may see that as f increases, the number of cycles increases. Now let's observe these plots till certain point. You may observe that this plot after 0.5 are getting repeated. You may see that the plot for 0.6 is equals to the plot for 0.4. the plot for 0.7 is same as that of the plot for 0.3. You may see that these two plots are the same. Similarly, the plot for 0.8 is same as that of the plot for 0.2. So the plot for 0.5 is the pivotal point after which the graph repeats in a reverse direction. So if you look at the plots from 0 to 0.5, they are unique, but after 0.5 onwards the graph repeats. You may see that the graph for 0.6 here, if I zoom this, the graph for 0.6 is the same as that of the graph of 0.4. Similarly, the graph for 0.7 is the same as that of the plot for 0.3, and so on. And at the end, you can see that the plot for f equals to 1 is the same as that of the plot for f equals to 0. So this 0.5, small f equals to 0.5, acts as a pivotal point or the turning point after which the graph repeats in the reverse direction of the frequency. Let us analyze what is happening here. So what I've done here is to vary this f from 0 to 1, and I've seen that after 0.5 this graph repeats. So let's make an axis, say this is the axis with respect to which the axis for small f with respect to which I am varying the frequency. So let the starting point be f small f equals to 0, and this last point, let that be 0.5. So in the middle we have all those values as 0.1, 0.2, 0.3, 0.4 and 0.5. Now as soon as the graph crosses, this frequency crosses 0.5, what happens is the values that gets exceeded gets mapped to the previous values. So the graph for 0.6 here, for example, graph for 0.6 is the same as that of 0.4. Graph for 0.7 is the same as that of 0.3, and so on. So graph for 0.8 is same as that of 0.2. Graph for 0.9 is the same as that of 0.1, and finally the graph for 1 is the same as that of 0.0 or 0. So let's analyze what is happening here. You may see that here, say for example the small f here, say for example small f here is 0.6. So we are analyzing the case where the graph exceeds 0.5. So x of n becomes cos of 2 pi 0.6 n. So we can represent that as cos of 2 pi 1 minus 0.4 n. Well, nothing wrong is that. So this is as good as cos of 2 pi n minus 2 pi into 0.4 n. And we know that the integer multiple of 2 pi in the angle will give you the same angle. So it gives cos of 2 pi 0.4 n. So you may observe that the 0.6 frequency is getting mapped to 0.4, as we have seen here. The 0.6 frequency is getting mapped to 0.4 here. So if we try to plot this visualization of mapping, we'll get something like this. So on the x-axis or the horizontal axis, if I'm trying to plot small f, so let this be small f with the values varying from, say, for example 0 onwards. So I'll have a graphical background. I'll draw it again. So I'll have an axis, horizontal axis, as f that increases towards right. So let it start from 0 and let that be 0.1, 0.2, 0.3, 0.4, 0.5 and so on, 0.6, 0.7, 0.8 and so on. Now this small f here is the values that it takes, actual values, and on the vertical axis let's plot the values that are getting mapped automatically. So what I'm saying here is the small f on the horizontal axis is this one. So let me say that it is small f here, and the actual values to which it is getting mapped, let it be fa. So vertically I would like to plot fa. So we have seen that this f is equals to fa as long as it reaches 0.5. So for small f equals to 0.1, you'll get the same value as 0.1. Now on the vertical axis, as I said, I am plotting fa. For small f equals to 0.2, we get fa equals to 0.2. Similarly for 0.3 and for 0.4. At the end, at 0.5, we get the final dot. So all these values are getting mapped correctly from 0 till 0.5. Now, as we have seen in the previous case, that as soon as the argument here, the f, small f, exceeds 0.5, what happens is we may express that as 1 minus that something, and the value to which it is getting mapped, that is small fa, is actually the lower frequency. So 0.6 here, the frequency after 0.5 is getting mapped to the frequency lower than 0.5. So 0.5 plus something is getting mapped to 0.5 minus something. So 0.6 is getting mapped to 0.4, 0.7 is getting mapped to 0.3 and so on. In fact, in negation. So I'm expressed that as something like this. So after 0.5 here, as soon as the 0.6 comes, at this point it goes in negation. So we may draw that as, so here, if this is the 0.5 point, then at 0.6 it would be here. So this is the point as minus 0.4 and the last point as minus 0.5. So on the y-axis I'm plotting, or on the vertical axis I'm plotting FA. So this is minus 0.1, this is minus 0.2, this is minus 0.3 and so on, minus 0.4 and minus 0.5. So there are some markings here that I am making. So it is minus 0.1, 0.2, 0.3, 0.4 and 0.5, yes. So as soon as this graph exceeds 0.5, the higher values are getting mapped to lower values. So the graph will look something like this. You may see that here 0.6 is getting mapped to minus 0.4, 0.7 is getting mapped to minus 0.3, 0.8 is getting mapped to minus 0.2, 0.9 here, which you may see that here 0.9 is getting mapped to minus 0.1, and this goes on. This things goes on. So there is a sudden transition here at 0.5. So 0.5 here, as I said, is a pivotal frequency, after which this frequencies repeats. Well, what does that mean? And we have named this the new frequency to which it is getting mapped as FA, or that is also called as aliased frequency. You may see that here 0.6n, 2 pi 0.6n is the same as that of 2 pi 0.4n. That means the new signal FA, this new signal with frequency FA, is the same that of the original signal F. So both of these signals, the one with 0.6 as F and the other one as 0.4 as FA, are the same. They are the equal signals. But here, if we look at the mapping, both of these signals are getting mapped to some different points. Although the frequencies appear to be different, they get mapped to the same frequency, that is 0.4. That's why we say that the signal is getting aliased. So 0.6 is the same as that of 0.4. So there are two different faces of the same signal, you can say. That is kind of aliasing effect that we can observe through this small f calculations. Now, what is its physical significance? For that, let's watch a video. I'm playing this video from YouTube. The video name is Wagon Wheel Effect. Now this video demonstrates how this frequency is getting mapped. Now in this video, as I play, the camera is set up on the wheel of a car and it is recording the revolutions that the wheel takes as the car proceeds. Now when I play this, you may see that the wheel is going forward and it appears that the wheel is again coming backward and forward, and it shuttles between the forward rotation and the backward rotations. You may observe here that the wheels here, sometimes it goes ahead, sometimes it goes back, and so on. Although the car is moving ahead, it appears that the wheels are rotating in the backward direction. You can see that here. So as the speed increases, it appears that the wheels are rotating backwards. So that is what is called as a wagon wheel effect. So I'll escape this. So that is what is called as a aliasing effect. So as the car speed increases, and it goes beyond 0.5, okay, the car rotation speed, the wheel rotation exceeds 0.5, then it appears that the wheels are rotating backwards. Therefore, the goes in negation. So that's the physical significance of aliasing, and we actually experience that in day-to-day life. What does this mean? The small f here is having limited set of frequencies, after which the higher frequencies are getting mapped to the lower frequencies. Now we can clearly see the range of small f to be from minus 0.5 to 0.5. That's the range of small f. Because after 0.5, the frequency would be the same as that of the frequencies in the negative range. So this is very important observations that we are making now. The range of small f, the discrete frequency, is very limited. Although it is continuous from 0.5 to minus 0.5 to 0.5, the limits, the upper cap here is 0.5. Well, this wasn't the case with capital F. The capital F, that was analog frequency, was not having such restriction. In fact, capital F can be varied from minus infinite to plus infinite, as long as the system can handle. F, the capital F, is the analog frequency that is having the range all the way from minus infinite to infinite, but small f, that is the discrete frequency, is having the range from minus 0.5 to 0.5. This means that after discretization of the signal, if we cut down the signal, after we discretize the signal, the range of the frequency is limited. It is from minus 0.5 to 0.5. We shall look more into this in the next module.